led by Martinović. We were doing the very far advanced simulations, and actually Deborah's talk was very nice because it gave a very nice introduction and lots of new stuff. So here I will talk about my recent results. After me there will be by the small Martinović and Stanislav Milošević and everything, which will talk also about armor together. So here we talk about actually the Lucid simulation and formation of compact Dwarf candidates, that is compact elliptical galaxies from clusters of galaxies. So basically, we actually exploit the situation that we have this logical simulation that goes into the dynamical regimes where we can actually see what's going on with the Dwarf galaxies as such. So first, a little bit about compact ellipticals. Well, compact ellipticals are M32 like Dwarf galaxies. So basically, they have 10 to the 10 mass of sun. They have no gas. They have no star formation rate gas. Very little dark matter inferred, and they have a half-mass radius that are really, or half-life radius that are really small. So basically, they are below 1,000 parsecs. So very hard to observe in the sense that for a very long time there were only a couple of M32-like objects familiar or visually observed, and considering that dynamical resolution of cosmological simulations was not high enough, they were not probably simulations as well. But that all changed in the past 10 years or so. A lot of them have been discovered observational, and as I said, we try to go the top range of those simulations. So basically, our motivation for the work were this paper here by Jean Gandel. Actually, the paper became available on archive in somewhere in the second part of 2016. They had a very nice idea where they used the Clash observations, basically, which became publicly available, and they checked scopically Clash objects which were ruled out as point source targets. They checked their kinematics in reference to the parent cluster which were observed, and as such they found, and of course due to the optical signature, they found that a significant number of compact ellipticals in 17 galaxy clusters in these redshifts. So basically they estimated the number of compact dwarfs in shells around going from the center of the most massive object in the cluster. So actually that gave us, we were doing something, for my PhD, something dynamics of the dwarfs, and that gave us the idea to check actually the same regions within the velocity simulation to see if there are candidates which would satisfy, which would be, which would correspond to their findings. And luckily we actually found 19 objects. So basically, as you can see here, this is the data from the Norris et al., which basically created a list, the plot of all the Dwarf galaxies known from different surveys, and they changed, they separated it on on by Dwarf type. So basically, in red here are shown the global clusters down here, UCDs down here, and compact ellipticals out here, where blue are Dwarf ellipticals, and here those variables as such. Now, considering that this plot is half-light radius, we were using half-mass radius. We found objects that are compact in half-mass radius, and that should be, when transferred to the half-light radius, should go down the scale size, down dips or X. So basically, we found two groups. One which were, because we had a situation where we could check the history of those objects. One group were externally formed massive galaxies that got heavily stripped while entering the cluster, and the other were surprisingly insignificant compact object which survive for until redshift 0. So basically, here, because I talked a lot during the past year about this, I will just briefly talk about the thing that I didn't cover a lot. That's the process of the extraction from the illustrative simulation. So basically, one of the advantages of the illustrative simulation is that it has both particles. Basically, all data is publicly available, which is really nice. Next to the Halo catalogs and merger trees, we had access to the particle data, which proved crucial for discovering these objects. So basically, using the Jean-Vidal observation data, we put some constraints for finding compact objects, which were less than 1 kiloparsec in half-life, and which were 100 kiloparsecs away from the most massive galaxy in the cluster of galaxies. So we found actually 23 objects in total in the clusters of Galaxies. Out of those 23 objects, further analysis showed that 3 are actually were at the detection limit of Halo definition, and they didn't have any history or connection to the previous or halos from the previous snapshot. So basically, we were ruled out as numerical artifacts. One was actually a supermassive black hole with 2 stars around it, which was free floating in the galaxy, which was quite interesting. We are doing further research about how many of those objects are there in the galaxies as well. But the 19 which were remaining were compact objects which had enough resolution in particles and information, especially information to the previous section. So checking the merger tree, it showed that only 2 objects had previous existed as with some history in the merger tree. And actually, those 2 objects helped us check the merger, create the merger tree for those objects themselves. Because if we didn't find any, we would just say this is all numerical artifacts. Those 2 actually gave us enough motivation to put in. So basically, we extracted the information including the particle data. One of the important things, most of the objects at the redshift 0 were actually having only, mostly or only stellar particles. That is probably, we assume that's the reason why the illustrative scheme or their pipeline for detecting the merger tree or information history of the halos didn't pick up those objects as well. Because if I'm not mistaken, those pipelines mainly use dark matter particles as the connection between surface and halos in different times. So basically, we took the objects of redshift 0, we took their position of the object, velocity of the object, particle IDs, and type of the particles present in the object. So after that, we took the information about the time interval between the snapshots, and within that time interval, we tried to calculate simply where the object would be in the previous snapshot. Then we would go into that small part of the snapshot, simulation volume, and we will try to find the objects which had the same particles with the same particle IDs as the previous object. If we didn't find any, we would just increase the search radius until search radius that was pretty large, for something like 400 kiloparsecs or so. So basically, usually we would find several objects, then we would check number of particles which were present at those objects, and the number of particles usually became very large. So basically, between 80 and 90% of the particles between objects were consistent. If no object was found in the previous snapshot, and of course we will do that. We will do that hopping throughout the simulation toward the beginning of the simulation as well. And thus we collected information about the between. If there are no particle IDs with the same type, we will of course check the other types as well. One of the interesting things is that if you come across the dark matter, enough of the dark matter particles and all the most of the actually objects had enough, at some point enough dark matter particles, you would just skip because you would find similar information in merger tree because it's connected to small patches of history. So if no objects are found, then we check not the previous, but the one before that as well, and the other one before that as well, just to check if the KL finder didn't skip or detecting the KL question, because that sometimes happens. So at the end, ultimately we were left with the merger tree, or merger branch, because we just took the primary merger branch for the selected objects, and we extracted information about their evolution, which showed that external, and that's how we made a division between the externally informed and in-situ formed. So externally formed are galaxies that had around Milky Way mass, okay, which after inflow into the cluster, they got tidally stripped and are left with dwarf elliptical, compact elliptical like total mass, where, as you can see here, most of that mass is are stellar particles. On the other hand, we have these objects which were created inside the clusters. They received some tidal stripping, but the thing is, it wasn't such a strain as before. So basically, this sums up what was happening. So all external population start their evolution as the normal on the CDM galaxies with 20-80% of this gas and dark matter. They form stars. They grow larger, and upon this is the distance. This is the distance relative to the cluster. When it's below 1, it enters the cluster. So basically, you see here that at some point they enter the cluster and they become the satellites of the most massive galaxy in the cluster. And at that point, you have the start of the tidal stripping process. So this was actually the result that we were most excited about, because this result showed what was assumed for complex ellipticals from the observations, and the assumption was that complex ellipticals, at least part of them, were created by tidal stripping of giant galaxies, which fell into the clusters as such. And the thing is, and like I said, we've shown it for the first time in small simulations. But this was the starting result. We had a situation where we have on smaller redshifts, so these are the redshifts of between 1 and 2, we have an injection of gas into the cluster. For some reason, that gas, probably due to cold multiplication on a cluster scale, that gas becomes creates a dense environment where, because it's cold, it starts in the densest part starts forming the stars. It creates stars, and the rest of it is tidally stripped, and you have the remaining complex elliptical object, which is that. So basically, these here, because our reviewer had a lot of interest in how this happens, so we created this. This is not the same snapshot, but this is the earliest time we detected the complex elliptical objects in situ form. So basically, you have here, for example, a situation where you have a very large, cold, low metallicity H1 rich cloud of gas that didn't exist as such in previous snapshot or anything like that. So basically, inside the cluster, so basically it was pumped into the cluster. Then you have at some point star formation within that part, the densest part, where it starts heating up and using gas. And this here, this shows that it probably gets blown away. And in the end, you are left with, so basically these are tens of kiloparsecs, 30 to 60 kiloparsecs. But in the end, you're left with something like this, and this is few kiloparsecs. Just the dense core remains with high temperature, no gas available, and high metallicity, which is not shown. Here is the different major difference. So basically, this, although we don't see each of these steps for each of the objects, considering the time between the snapshots, considering that we have different snapshots for different different practical status or different earliest in situ compact ellipticals, we could assume what was going on as such. So basically, those were the two results. So in situ and external population from the results were used. It would be interesting to see if this survives in other simulations as well.
Do we have some questions? If not, thank you.